started. I'd like to start, also remember the QR code is at the beginning of the presentation. Okay. I'd like to start to exploit better the title of my presentation. So, first of all, what is the structure interaction problem? Okay. Sorry for the delay. I didn't know that the if we were going to land, but anyways. Okay, three-step interaction, we have three main agents in action. There is the fluid problems, in this case the water, okay, and there is the solid problem, in this case the ship, and lastly there is a coupling between these two problems, because these two problems need to speak with each other, okay. On the left there is a small representation, schematic representation, in particular from the solid problem we want to extract the displacement, or in this case the velocity, and pass to the fluid. And at the same time, we want to compute the forces acting on the interface and pass them to the solid. This is computed recursively until a convergence is reached. Okay. The second part of the title is structural elements, lightweight structures. What are lightweight structures? I want to about with some examples. The first example is the dragonfly wings. We can discretize these dragonfly wings as membrane elements, for example, or shell elements. And at the same time, also the veins on the wings can be modeled as beam elements, so one-dimensional structural elements. So these altogether can be simulated in a fluid code. Another example could be like the sails. Okay, this is a small video about a maneuver. Okay, you see that on the sail there is the wind acting, but at the same time the sail has a negligible thickness, and the fluid is on both sides of the sails. So this structural element has to be account for forces acting on both sides of the structures. So this is the kind of example that I'm considering during my research. I don't want to stress you with all the benchmark to see validation of the method. I pass directly to the main example done before. That's just one slide about technical stuff. I'm going to solve Navier-Stokes equation, okay, in Arbitrary Lagrangian-Eulerian framework. U is the fluid velocity, W is the domain velocity, because we are considering the case where the domain is moving. Sigma is the stress tensor, the Cauchy stress tensor. Rho is the density of the water, of the fluid. F is the external forces. And we are imposing divergence free, meaning that we are considering incompressible fluid. Some modelization choice, okay. We are considering Newtonian fluid. So this is the classical Cauchy stress tensor for Newtonian fluid, where P is the pressure and mu is the dynamic viscosity. And we need to take in account also some scenario where the mesh will be poorly resolute around the object, and so we need to somehow speak about how to recreate the mesh when the mesh is too distorted. And at the same time, we need to account for this structural element immersed in fluid. Okay, I don't want to stress a lot. I will tell you with example what I deal with this. And lastly, just because I'm from mathematical background, I have some mathematical stuff. I'm using finite elements method. That's the poster stuff to tell. The other stuff is that the mesh is composed by tetrahedral that always has straight edges, and also solving with some stabilization to take into account a high Reynolds number. For the mesh, just to make you also hear an example, okay, there is a scenario where the mesh is too distorted. For example, next to the tip of this rotating disk, the mesh is too distorted, and the simulation cannot go further in time. And in this kind of situation, what we are computing is through mirror meshing, and this meshing is based to this quality mesh indicator, where vol is the volume of the tetrahedra, and AI are the lengths of the edges of the tetrahedra. And maybe it's better to see. Here is where the simulation is stopped because the elements are too distorted, and there is when we compute the mesh again after this procedure. And so here where we stop at the beginning, and there is what we can do now. So we are able to simulate large displacement and large deformation in this setting. And here is the main part, the dragonfly modelization. Okay, why we choose to model the dragonfly among all the insects in the nature? Because dragonfly is endowed with two different pair of wings, and this allows them to perform high aerodynamics maneuver, and also it allows them to have a high controllability in hovering, and they are also used for micro air vehicles that are applied in environmental monitoring. And here is the picture of the dragonfly, and there are the two wings that are on the dragonfly. They named out four wings and hind wings. And the hind wings is larger, and the forewing is smaller. And this is the modelization that we decided to make in the solid part. For more detail, as I said before, we discretize the wings with membrane elements. Okay, there are all the material specifics, and for the base, we decide to use beam elements, so unidimensional elements. And there we can see the mechanical properties, but also we see that we distinguish between primary and secondary veins. The difference is in the thickness of these veins. Of course, the more we are on the top, the more the veins are thicker, and we also include this modelization. And lastly, to make everything more realistic, we impose some hinge constraint in the dot point, in order to allow the mutual movement between the different parts of the wings. Here we can see the simulation for one single wings. We take in account the hind wings. Okay, we use the as fluid hair, so there are the viscosity and the density of the hair. And what we impose from the mechanical view, we impose a rotation, okay, with 30 degrees as maximal degree, and this is the frequency of flapping of the dragonfly. These are realistic value taken from paper, so I'm not simulating here. Okay, and you can see here, especially in this column, the pressure. You can see that there is a different pressure up and above the surface. This is how we deal with this surface immersed in a 3D fluid. So we basically divide it between what is above and what is below the surface, and we treated them as two separate surfaces. Okay, so what is happening above doesn't speak with what is happening above. There is this wall with no dimension. It's a surface. Okay, and in the second column we can see some streamline, just to see some fluid simulation. And in the second row we also plot the voluminous and all the stresses on the wings. Okay, this was just some preliminary results to understand if the method was working in a realistic application. And after that, we move to complete dragonfly. So we include both the wings, and we also discretize with some solid part the body of the dragonfly. Of course, we are smart, and so the dragonfly is symmetric, so we simulate half of the dragonfly. Okay, you can see here half of the fluid of the domain, and we also impose some realistic movement. Here are the movement of the hindwing and the forewings, and there is an initial angle of attack, and this rotation, and this is the frequency with a phase between them. So they are not moving together. There is a phase between them. All the data are there, and also there is some angle of attack on the wings. This is the video, lagging video. We compute that the Reynolds numbers is around 4K, and you can see on the left the mechanical deformation. Okay, as I said before, we simulate half of the dragonfly, the other one is mirrored. So these are the mechanical part, and there are the streamline on a plane that is cutting both of the wings. Okay, you can see that there are a lot of vortices forming around the wings, and there is a visible deformation. Okay. The second application, that is something that is also preliminary, but we are still working on nowadays with the collaboration of the polyimide saving team. We are simulating the main sheet deformation. Here you can see two sails, and we impose an inflow, and we can see the streamline around the sails, and on the sail you see the stresses. On the right, there is this small animation of this small mechanical model that we are trying to implement, where we try to improve the discretization of the model of the sails. You can see that we impose much more boundary condition. In particular, there is both the main sheet, there is also the boom. Okay, and you can see that in this small animation, there is this pressure applied on the sails, and at a certain point, the pressure changes direction, and the boom is following the sails. So there is this interaction between the parts. And of course, our final goal is to apply also FSI of this kind of simulation with the help of the sailing team. Lastly, okay, is the application that I developed during my period abroad. In particular, I spent 3 months in the UGent for developing some free structure interaction model for hydrofoils. The hydrofoils are, for example, here are some images of my hydrofoil that are basically the one that you see in the first slide about Luna Rossa. Okay, these are very, very simpler hydrofoil. There are different parts we want to simulate all together, and all this part that I will speak to you later. What does it mean? Everything. Every part is made of an extrusion of a profile. Okay, and the profile are the so-called NACA profile that are very famous in the literature. Okay, and you can see that this profile is symmetric. This profile is not symmetric. Okay, it's hard to see, but it's likely not symmetric. Okay, and if you impose a flow in this direction, here the overall forces will be 0 because of the symmetry. Here, because of the no symmetry, there will be a lifting force. And it is the phenomena that is behind the hydrofoil, and the reason why the Copa America ship is lifting from the water. Okay. Here are all the components. There is the rudder. Okay, the purpose of the rudder is to give the direction of the ships. Okay, the elevator. These are not lifting surfaces, just there for regularization purpose. And then there is the main foils. The main foils here are the ones that are creating the majority of the lift. Okay, and that's why these are symmetric and these are not symmetric, because we want that main foil to create the majority of our lift. And what we expect is that increasing the velocity of the ship will take off, okay, due to the lift. And when there is enough lift force, the hull of the ship will be not in contact with the water. And so this is why they are going much faster than normal ship. there are two different way to solve this problem. There are this low fidelity model. It's called vortex-latex models funnel method. Okay, from there we can compute with low effort the lift force that we want, but also the pitch moment. The pitch moment is the force that creates the rotation of the ships. Okay, nothing about this table. Okay, we use this low fidelity model to compute some preliminary results on the hydrofoils, and you can see that here we increase the velocity, and increase the velocity, the forces are quadratic as expected, and the red line are the weight of the ship and the momentum generated by the sails. So if we are going faster than between 4 and 6 meters per second, the lift force will be higher than the weight of the ship. So there will be a lift of all the structures, and this is what we want. We want to find the lift, a positive lift of all the structure. And what we want also, we want to also study the final position, where basically here is the configuration where everything is zero force. So this is the flight mode. And here is just some analysis of stabilization of the equilibrium. But there is one piece that is missing of all this part, and we are not considering deformation. And the deformation is very important because if my foil is deforming, all the structure is deforming, and also the lifting surfaces will not generate the same lift as expected. So the deformation has to be taken into account, and to do that, we start developing some high fidelity model. So we start from zero, and we decide to model everything from zero. In particular, here is the section of some foil. They are composed from a core material and some skin around them. Okay, and you can see that it's what we've made. There's this core material and skins around them, and these skins, in particular, is composed by some composite materials. Okay, taken from the literature. This I just reported all the ply of the composite materials with different direction of the fiber. Okay, this is CUD, is carbon fiber, unidirectional. This is what we have done from the mechanical point of view. Of course, we also need something from the fluid side. Okay, so we are using Fluent for performing all the FSI environment. In particular, you can see that we create a box around the hydrofoils. We impose an inflow and an outflow, and here is my hydrofoil from the fluid side. Okay, these are just some fluid setting. We are using some turbulent models. We are solving just the water, and the inflow is between 1 and 5 meters per second because the target is around 5 meters per second. And for the coupling, we are using this coconut library that is developed from Uganda University. There's a why I went there. And lastly, you can see some preliminary results. It's something that is still going on. We can see that working. There is a deformation, not negligible deformation, because there is no any there is a two times, but not that much. Okay, the deformation is not negligible. Okay, so the deformation has to be taken into account. This is from in front, and this is from above, and so the deformation has to be taken into account. And we want to continue to perform simulation on this point. And lastly, what's next? In the meanwhile, I'm developing a two-phase solver and to perform some two-fluid simulation like the two-fluid sloshing that you see here. Basically, each color is a separate fluid that interact with each other with interface. And the final goal is to apply this phase to form water hydrofoil. So to take in account also the air, and so to perform a complete two-phase of the hydrofoil from the beginning to the final configuration. Thanks for your attention, and if you have any questions, I'm here to answer.
I'm interested in the dragonfly wings stresses